Here's area estimation for VCE methods in less than a minute. The first method that we have is the left point estimate. What this method does is it makes rectangles underneath our function for our desired area, but it connects the rectangles to the left side of the function. So what I mean by that is each rectangle that's created, so for example, the first one from x equals 0 to 1, the left point, which is x of 0, that's connected to the function. From 1 to 2, the left point at x equals 1 is connected. From 2 to 3, the left point at x equals 2 is connected to the function. Okay, so this is our estimate method. You can see the shaded area is our area approximation, and you can see there's some gaps there. Obviously, the method isn't perfect. It's called estimation on purpose. It's not meant to be exact. So when we calculate this area, what we do is we just calculate the area of each of the rectangles and add them together. So the base is always 1, and usually it's chosen as like a consistent number. So the first area is 1 multiplied by the height, which is f of 0, again because the left point is connected, and then 1 multiplied by f of 1, 1 multiplied by f of 2, and that's all added together. So we get, when we substitute in 0 into this function, we get 0 squared plus 1, which is 1. If we substitute in 1 into this function, we get 1 squared plus 1, which is 2. We substitute 2 into the function, we get 2 squared plus 1, which is 5. So our final area estimate is 8 units squared. Okay? Now, for the second method, we have the right point estimate, and you can see it's exactly the same method, except for each of the rectangles, the right side is connected to the function. So from 0 to 1, the point at x equals 1 is actually connected to the function. The point at x equals 2 is actually connected to the function for this one. The point at x equals 3 is connected to the function for this width there. So the calculation is very similar, except you can see the numbers are slightly different. We've got 1 multiplied by f of 1 for the first rectangle, and then f of 2 for the second rectangle, f of 3 for the third rectangle. So f of 1 was equal to 2, f of 2 was equal to 5, and f of 3 is equal to 3 squared plus 1, which is 10. So our final area actually ends up being 17 units squared, which is almost double this one. And the reason why it's almost double is because you can see it's a very big over approximation. So you can see this area is above the function, this area is above the function, this area is above the function as well. So both of them aren't the best estimates. You can see this one has error, this one has error as well, but they have error in different ways. This method causes an under approximation because this graph is increasing. You can see when you're increasing, when your function is strictly increasing, what happens is when the left point is connected, you're creating a gap that is under your area. Okay. Now, when you have a strictly increasing function and you're using the right point estimate, you can see you have an overestimation because your area is obviously above. You can see this area is above here, this area is above there, and this area is above the function as well. So depending on if your function is strictly increasing or strictly decreasing, you're either going to have an over approximation or an under approximation. Now, if you're ever asked in a SAC to kind of think about another way of making these methods better, one way is to use the trapezium method. Now, the trapezium method is a method where instead of creating rectangles, you actually create trapeziums with the left and the right point for each of your widths. So for example, if I have 0 to 1 here, what I do is I can actually make a trapezium that just is a connected line between the function at 0 and the function at 1. And what will happen is it will just allow for some angle when you're connecting the points, and that means that you can follow your function a lot better, especially for curve functions like this one. Another way of improving your estimation is by making your width smaller. What a smaller width would do was it would just mean that you could get closer to the function. So if I split up the 2 and 3 into 2 to 2.5 and then 2.5 to 3, this is what happens. You can see that my error is kind of small because I can include this bit as well now. So my error is only here and here when before it was that big triangle in there. So that's another way of reducing your error when you're using the estimation method.